Okay, in this video, we're going to talk about section 8.4, dealing with testing a claim about a standard deviation or variance. So already in chapter 8, we talked about some of the basics of hypothesis testing, and then we talked about how to test a claim about a population proportion and also testing a claim about a population mean. This time, we're going to look at how we can test a claim about a standard deviation or variance. And in this section, we're going to use sample data to conduct a formal hypothesis test of a claim made about a population standard deviation or variance. Okay, so what we're going to look at is just some methods for conducting a formal hypothesis test of a claim made about a population standard deviation, sigma, or population variance, sigma squared. Okay, and the methods that we'll be using will be the chi-square distribution. Okay, so here we're going to talk about some of the things we need to know about testing a claim about sigma or sigma squared. And we'll start with the notation here. Lowercase n is the sample size, lowercase s is your sample standard deviation, and of course the sample variance is s squared. And then sigma is going to be the claimed value of the population standard deviation, and sigma squared is going to be the claimed value of the population variance. Okay, now here's some requirements that you're going to need to know, and there are only two of them. One is that the sample is a simple random sample, meaning that samples of the same size have an equal chance of being selected. And then number two, the population has a normal distribution. Here, instead of being a loose requirement, this test has a very strict requirement of a normal distribution. And this is the test statistic that we will use for testing a claim about sigma or sigma squared, and that is the chi-square. Chi-squared will be equal to n minus 1 times the square of the standard deviation divided by the square of the population standard deviation. Okay, now our chi-square values, we're going to round to 3 decimal places as in table A-4. Okay, now we should already be familiar with table A-4 from section 7.3, I believe. Okay, so here, this is table A-4, the chi-square distribution. Those values are to 3 decimal places. So when we find our chi-square test statistic, we're going to round to 3 decimal places. Now the p-values, we're going to use technology. It'd be best to use technology, mainly the TI-84 plus calculator, which I'll be using here in this video. Now, and of course, our degrees of freedom will be given by df equals to n minus 1. Okay, and if you were using table A-4, it's always the cumulative area from the right. All right, next we'll look at, now don't worry about the critical values in this video, okay? Because the critical values you have to use table A-4 with degrees of freedom given by df is equal to n minus 1. And table A-4 is going to, again, will be based on the cumulative area from the from the right. All right, now for the properties of the chi-square distribution, now some of this is kind of a review over some of the things we talked about when we were doing the confidence interval for a population variance or population standard deviation. All the values of chi-square are non-negative, and the distribution is not symmetric. And number two, there is a different chi-square distribution for each number of degrees of freedom. And number three, the critical values are found in table A-4 using n minus 1 degrees of freedom. Okay, so that's the illustration of what the chi-square curve looks like. And of course, the chi-square curve in blue is for 10 degrees of freedom, and the one in red represents 20 degrees of freedom, your chi-square distribution. Okay, don't get the chi-square distribution confused with the normal distribution. Okay, because if you look at if you know table A-2 provides cumulative areas from the left, whereas in table A-4 for the chi-square distribution we use the cumulative area from the right. Okay. Now the p-value method, which will be the best way to use, the best thing to use here in these examples I'll be providing. Okay. So we'll be using the TI-84 plus calculator, and that's pretty much it. And I'll show you how to do the manual calculations with the p-value. So once you find your test statistic and your number of degrees of freedom, the p-value can be found using the TI-83 or 84 plus calculator. Here's a procedure. You have to press second and bars to get to the distribution menu. And then from that menu, you'll select chi-square CDF. Okay. Now the chi-square CDF command requires 3 items separated by commas in this format. Now this is if you have the TI-83 or the earlier TI-84 plus calculator, because they'll give you chi-square CDF on the left side. And then you have to enter the lower bound separated by a comma, then the upper bound separated by a comma, and the number of degrees of freedom. Okay. Now in this case here, here's how we find the p-value using the number of degrees of freedom and the test statistic as shown below. If you have a left tail test, then your p-value is going to be the result of this. After you select chi-square CDF, your lower limit would be a negative with, and I have 6 nines, but you can use as many nines as you need to get a more accurate p-value. So it'd be negative with, let's say, 6 nines, and then your test statistic, then degrees of freedom. But for a right tail test, to find the p-value, you're going to still use chi-square CDF, but this time you'll enter the test statistic first and then at least 6 nines, because right tail goes on forever, and then degrees of freedom. But however, if you have a two-tail test, your p-value is going to be the smaller of these two results, and that's going to be this, twice the value obtained from this. A negative with 6 nines, then test statistic, then degrees of freedom under the chi-square CDF command, or 2 times the value obtained from this, the test statistic, and then 6 nines, and then degrees of freedom under chi-square CDF. You're going to pick the smaller of the two for a two-tail test. And why we do twice? Because it is a two-tail test. Now for the confidence interval method, when you're using claims about sigma or sigma squared, the p-value method, the critical value method, and the confidence interval method are all equivalent in the sense that they will always lead to the same conclusion. Okay. Okay, so let's look at a few examples of just this and how to use that chi-square CDF command. All right, in example 1, it says this: a simple random sample of 30 men from a normally distributed population results in a standard deviation of 11.4 beats per minute. The normal range of pulse rates of adults is typically given as 60 to 100 beats per minute. If the range rule of thumb is applied to that normal range, the result is a standard deviation of 10 beats per minute. Use the sample results with a 0.05 significance level to test the claim that pulse rates of men have a standard deviation equal to 10 beats per minute. Okay, so if we use that 8-step hypothesis testing procedure, we should be able to answer parts A, B, C, and D. And if you're not familiar with that 8-step hypothesis testing procedure, refer to the video for section 8.1, dealing with the basics of hypothesis testing, because that's the video that has that 8-step procedure that I showed you. Okay, now let's go through that 8-step procedure. In step number 1, you have to identify the original claim and write that in symbolic form. All right, now we're testing the claim that the pulse rates of men have a standard deviation equal to 10 beats per minute. So in symbolic form will be this. Our standard deviation, we're using the Greek letter sigma, and then that's equal to 10. That's the original claim. And then step number 2, we write the opposite of the original claim. Well, the opposite of equal to will be, of course, not equal to. So this will be sigma is not equal to 10. That's the opposite of the original claim. And then step number 3 is to write our null and alternative hypotheses. All right, keep in mind the alternative has either the not equal to, greater than, or less than. This is not equal to, so that means sigma is not equal to 10 has to be your alternative hypothesis, whereas sigma is equal to 10, that's going to be the null hypothesis. And that's also the claim, as you can see in step number 1. So that's why I put the word claim in parentheses. And then step number 4 is identifying the level of significance. In this case, we're using the sample results with a 0.05 significance level. So that's step number 4. And now step number 5 is calculating the test statistic. And we're using a chi-square test statistic since we're dealing with the standard deviation. Okay, now let's identify what we have here. We have a simple random sample of 30 men. So your N is going to be 30. And we have a standard deviation of 11.4 beats per minute. So S is equal to 11.4. And let's go ahead and find out what our degrees of freedom is. That's always N minus 1. N is 30, so 30 minus 1 is 29. So we're going to be dealing with 29 degrees of freedom. And then sigma, that comes from the null hypothesis. That's going to be 10. All right, and our chi-square test statistic is this. Chi-squared is equal to N minus 1 times S squared, all divided by sigma squared. So we just substitute into that test statistic formula. N is 30, so this will be 30 minus 1 times S, which is 11.4, and that's squared. All divided by sigma, which is 10, and that's squared. All right, so now let's put this in our calculator. All right, let's see here. I'm going to put the 30 minus 1 in parentheses. So this will be 30 minus 1. That's in parentheses. And keep in mind your parentheses is above the number 8 and number 9 keys. And then that's multiplied by 11.4. And that's going to be squared. So we press the X square button to square that, divided by 10, and then the X squared. And then finally hit enter. Now our test statistic For chi-squared, we round to 3 decimal places. So this will be 37.688. 37.688. Okay, so that will be the test statistic here for this sample data. Now, step number 6 is finding the p-value. And that's the probability of getting a test statistic that is extreme as the one that we've obtained from our sample statistics. Now, take a look at your alternative hypothesis. That's going to tell you whether or not you have a two-tailed test, a left-tailed test, or a right-tailed test. For not equal to, it is a two-tailed test. Now, if it was less than, then it's a left-tailed test, or if it's greater than, it's going to be a right-tailed test. Okay? Since it's a two-tailed test, we have to take the smaller of these two. So the way we have to do this, we have to do 2 times because it is a two-tailed test. So that means we have to do 2 times and then chi-squared CDF and then negative with at least 6 nines here. And then the test statistic, 37.688. And then my degrees of freedom, 29. And I want you to know that I'm following this format right here. For a two-tailed test, I have to take the smaller of these 2 cases here. I have to find out what this value is going to be and also what that value is going to be, and then take the smaller of the 2. That would be my p-value. And it's going to be twice the value because it's a two-tailed test. So that's why you see 2 times this. So this is going to be 2 times, and I'm going to do this in the calculator so you'll see what I'm doing here. Here you have to press second and bars for your distribution menu. Second and bars gives you the distribution menu. Underneath that, you have to use your down arrow key to select this item, chi-square CDF. Then I'm going to press enter. Now, the lower limit is this. So it'll be negative with as many 9s as you want. I'm in this case using 8 9s. And then go down to your upper, which is that test statistic, 37.688. Then go down to your degrees of freedom, in this case is 29. And then highlight paste using the down arrow key or pressing enter. Press enter. It's going to look like this, so you'll press enter. Now, it's this amount, 0.8506, rounded to 4 decimal places. 0.8706. I'm sorry. Here it is, 0.8706. But I have to multiply by 2 because it's a two-tailed test. So I'm going to take that, multiply it by 2. You're going to get, in this case, 1.7411. And unfortunately, we're not going to be able to use that one because if you recall, probabilities are values that are between 0 and 1. This number is bigger than 1, so we're not going to be able to use that. So that means we have to do it the other way. The chi-square CDF, which is, in this case, this one. The test statistic, and then as many 9s as you need, and then the degrees of freedom. So my test statistic was 37.688, and then I'm just writing 6 9s, and then degrees of freedom. So I know I'm going to have 2 times. So here in the calculator, I'm going to do second and bars. and then use chi-square CDF again, hit enter. My lower limit is going to be that test statistic of 37.688. The upper limit will be as many nines as I want, and then enter. Degrees of freedom, 29. Hit enter to highlight paste, and then hit enter again. This will be 0.1294, but I have to multiply that by 2. So, multiply that by 2. So this will be 20.2588. Okay. And you know something, to be fair with this one, I'm going to say 1.7412 for this one. Not that it matters. Okay. But I have to pick the smaller of the two, which is the one that says 0.2588. All right. So here, the p-value will be 0.2588. That's the smaller of these two right here. All right, now, step number 7 is the decision rule. So the decision rule in step number 7 is this. If your p-value is less than or equal to alpha, you want to reject the null hypothesis. Now, the p-value is that 0.2588. And my alpha level from step number 4 is 0.05. As you can see, 0.2588 is greater than 0.05. So this does not satisfy the decision rule. So that means I need to fail to reject the null hypothesis. Okay. And then finally, step number 8 is my conclusion. Well, the claim was the null hypothesis from step number 3. And I failed to reject that claim. And that's because the null hypothesis was a claim, and I failed to reject the null hypothesis. So my statement will start off like this, that there is not sufficient evidence to warrant rejection of the claim. That the pulse rates for men have a standard deviation equal to 10 beats per minute. Okay. Right, so that's the 8-step hypothesis testing procedure here in this case. All right, take a look at example 2 in your handout. It says here the piston diameter of a certain hand pump is 0.4 inch. The manager determines that the diameters are normally distributed with a mean of 0.4 inch and a standard deviation of 0.005 inch. After recalibrating the production machine, the manager randomly selects 21 pistons and determines that the standard deviation is 0.0044 inch. Is there significant evidence for the manager to conclude that the standard deviation has decreased at the 0.10 level of significance? Okay, so here we're going to go through that 8-step procedure again. All right, so step number 1, we need the original claim. In symbolic form, we're saying that the standard deviation has decreased at the 0.10 significance level. And in this case, if it's decreased, it has to be less than. And the number that we're using here is 0.005. Okay? Because the manager determines that the diameters are normally distributed with this mean and the standard deviation of 0.005. That's the original claim. Now, step number 2 is the opposite of the original claim. Well, the opposite of less than had to be greater than or equal to 0.005. And then step number 3 is writing our null and alternative hypotheses. Well, if it's less than or greater than or not equal to, it falls under the alternative hypothesis. So this statement of sigma being less than 0.005 will be your alternative hypothesis. And that's also the claim. The null always has the equal to sign. So it'll be sigma equals 0.005. And now step number 4 is your level of significance. And in this case, it's 0.10. That's given to you in that problem. And now step number 5 is going to be calculating the test statistic. Let's see what we have here. We have 21 pistons that was randomly selected. So it would be N equals 21. We also know what our standard deviation of those 21 pistons, 0.0044 inch. And I'm also going to find out what my degrees of freedom will be, which is N minus 1. N is 21. So if I subtract 1 from 21, I get 20 degrees of freedom. And my sigma is going to be from the null hypothesis, the population standard deviation, 0.005. And then we'll use those sample statistics to come up with the test statistic for chi-square, which is, of course, N minus 1 times S squared, all divided by sigma squared. N is 21, so I'm going to have 21 minus 1 times S, which is 0.0044, divided by sigma 0.0, and that, oh, I've got the square, because 0.0044 is the standard deviation. That needs to be squared. And then sigma is going to be 0.005. That too is going to be squared. Okay, so let's see what we got here as the final test statistic. If I do 21 minus 1 in parentheses, and then times 0.0044, and I square that, then divided by 0.005 and square that, I will get 15.488, and it is exactly just 3 decimal places. Okay. So my test statistic there would be 15.488. All right, now step number 6 is calculating the p-value. Let's see, calculating the p-value. Now, if you look at your alternative hypothesis, that will tell you what type of test you're going to have. In this case, less than points to the left, so that means I have a left tail test. And in a left tail test, let's go back to this. In a left tail test, the result of the p-value will be this. During the chi-square CDF, I have a negative with at least 6 nines, then your test statistic, then degrees of freedom. That's going to be the format for that. So now my p-value is going to be equal to this, the chi-square CDF. Since it's a left tail, I have a negative with 6 nines, and you can use as many nines as you want. Make sure you have a negative sign in front of it, since it's a left tail. And then next is your test statistic of 15.488, and then your degrees of freedom is 20. Okay. So here I'm going to do second bars. Arrow down to chi-square CDF, press enter. The lower would be, let's see, the negative key is at the very bottom of the calculator. I forgot to mention that. And then as many nines as you want. And then use your down arrow key or press enter. My test statistic was 15.488. Then enter. The degrees of freedom was 20. So we type in 20. And then paste. Then hit enter again. This will be your test statistic. Your p-value. Now, if they ask for 3 decimal places, I would say 0.252. That would be the p-value. So your p-value is going to be 0.252. And p-value, of course, is a probability of getting a test statistic that is extreme as the one that we obtained from our summary statistics. And this looks like a 25.2% probability of getting a test statistic like the one here. Now, step number 7 is deciding whether to reject the null or fail to reject the null. That's our decision rule. If our p-value is less than or equal to alpha, reject the null hypothesis. Otherwise, you fail to reject the null hypothesis. So my p-value was 0.252 from step number 6. The alpha level was 0.10 from step number 4. Compare those two. You'll see that it is greater than our level of significance. It does not satisfy the decision rule, so that means we need to fail to reject the null hypotheses or null hypothesis. And then step number 8 is the conclusion. Well, we failed to reject the null hypothesis, and the claim was the alternative hypothesis. So that means we have to say that there's not sufficient evidence to support the claim. So here, there is not sufficient evidence to support the claim that the standard deviation has decreased at the alpha equals 0.10 level of significance. Okay. So that's the procedure here. All right, now let's look at example 3. Says here a simple random sample of 28 filtered 100mm cigarettes is obtained from a normally distributed population, and the tar content of each cigarette is measured. The sample has a standard deviation of 0.22 milligrams. Use a 0.05 significance level to test the claim that the tar content of filtered 100mm cigarettes has a standard deviation different from 0.35 milligrams, which is the standard deviation for unfiltered king-size cigarettes. And when you do that 8-step procedure, you'll be able to answer the questions in parts A, B, C, and D. Okay, so let's use that 8-step procedure. Okay, step number 1 is the original claim in symbolic form. Now here, we're testing the claim that the tar content of filtered 100mm cigarettes has a standard deviation different from 0.35 milligrams. So we have standard deviation at sigma. The phrase different from means not equal to 0.35. That's your original claim. If it's different, it means not equal to. We don't know if it's greater than or less than. We just say not equal to, because it doesn't give us what they call directional language. Now, step number 2 is the opposite of the original claim. Well, the opposite of not equal to has to be equal to, so this will be sigma is equal to 0.35. All right, and then step number 3 is writing our null, identifying the null, and alternative hypothesis. Well, if it's not equal to, it must be the alternative hypothesis. So that sigma not equal to 0.35 is the alternative hypothesis. Not only that, it is also the claim. And sigma equal to 0.35 has to be the null hypothesis, because the null hypothesis always has the equal to sign no matter what. And then step number 4, the level of significance. In this case, we're to use a 0.05 significance level. And now step number 5 is calculating the test statistic. Well, we got 28 filtered 100mm cigarettes as our sample. So N is 28. And the standard deviation for that sample is 0.22. That's S. And degrees of freedom. Let's go and get that. That's N minus 1. N is 28, so if I subtract 1 from 28, I will get 27 degrees of freedom. And I'll go ahead and identify sigma, which is 0.35. That comes from the null hypothesis. So now we can find out what that chi-squared test statistic is going to be. So chi-squared is going to be N minus 1 times S squared divided by sigma squared. And that's going to be equal to this. Substitution, N is 28 minus 1 times S is going to be 0.22, and that's squared, divided by sigma, which is 0.35. That too will be squared. All right, so left parentheses, 28 minus 1, close parentheses, times 0.22 squared, divided by 0.35. That too is squared. Hit enter. Enter. To 3 decimal places, this will be 10.668. 10.668. That's my chi-square test statistic. Okay. Now for the p-value, this is step number 6. Let's take a look at our alternative hypothesis. It says not equal to. That means it's a two-tailed test. So in other words, we got to take the smaller of this 2 times, and the 2 is for the fact that it's a two-tailed test. We have to do 2 times the value from this, the chi-square CDF, and then the lower will be negative with 6 nines, or as many nines as you want. Then your test statistic 10.668, and then your degrees of freedom 27. Or this 2 times chi-square CDF. First your test statistic 10.668, and then the upper limit will be at least 6 nines, and then your your degrees of freedom 27. It's going to be the smaller of these two values here. Okay. So let's start with this one right here. Do second bars. Use your down arrow key to get to chi-square CDF. Hit enter. Now, my lower limit will be a negative with 6 nines, or as many nines as you want to, but I've already got that there. You might want to type it. I'll go ahead and retype it. And then hit enter. Test statistic 10.688. No, 10.668. Then enter. Degrees of freedom 27. Hit enter to highlight paste, hit enter, and then enter again. This will be 0.0021. But you know it's going to be 2 times that. So it'll be 2 times. Let me write that 0.0021. So 2 times that, because it's a two-tailed test. This will be 0.0042. Or to 3 decimal places, 0.004. And I think that's going to be the p-value, because if I try to do this, and I'll go and do this just to show you, second bars, and then chi-square CDF, the lower limit is 10.668. The upper limit will be as many nines as you want, and then degrees of freedom 27. Hit enter 3 times. If I did 2 times this, it's going to be more than 1. Okay. So let me go ahead and write this out as 2 times 0.9979. You'll get 1.9958. So we know it can't be that, because the probability value can't be bigger than 1. So it has to be the 0.004. So here, this is what my p-value is going to be. 0.004. Okay. And now step number 7 is the decision rule. And that is, if the p-value is less than or equal to alpha, you want to reject the null hypothesis. And here the p-value is 0.004. The alpha level is 0.05 from step number 4. Compare those two. 0.004 is less than 0.05. So it does satisfy the decision rule. So that means we need to reject the null hypothesis. Okay. If the claim was the alternative hypothesis in step number 3, we reject the null hypothesis. That means we have sufficient evidence to support the claim. Okay. So step number 8, in simple non-technical terms, we say that there is sufficient evidence to support the claim that the content, the char content of filtered $100 millimeter cigarettes has a standard deviation different from 0.35 milligrams. Okay. Okay. So let me go back to this. In step number 3, that's the answer to part A. What are the null and alternative hypotheses? And then step number 5 was the tested statistic. That's the answer to part B. And then step number 6 was the p-value of that test statistic. That's part C. And then state the conclusion. Sometimes they have steps 7 and 8 combined in that. All right, finally, example number 4 states this. Workers at a certain soda drink factory collected data on the volumes in ounces of a simple random sample of 21 cans of the soda drink. Those volumes have a mean of 12.19 ounces and a standard deviation of 0.12 ounces, and they appear to be from a normally distributed population. If the workers want the filling process to work so that almost all cans have volumes between 11.95 ounces and 12.67 ounces, the range rule of thumb can be used to estimate that the standard deviation should be less than 0.18 ounces. Use the sample data to test the claim that the population of volumes has a standard deviation less than 0.18 ounces. Use a 0.05 significance level. Complete parts A through D below. So again, that 8-step procedure will be used here to answer parts A, B, C, and D. All right, so let's start with the first step. Writing the original claim in symbolic form. And we know that use sigma. Now it does say here that we're testing the claim that the proportion of volumes have a standard deviation less than 0.18 ounces. So this is the symbol for less than 0.18. And then step number 2 is identifying the opposite of the original claim in symbolic form, or writing the opposite of the original claim. The opposite of less than will have to be greater than or equal to. So it'll be sigma is greater than or equal to 0.18. And then step 3 is to identify the null and the alternative hypothesis. So in this case here, the not equal to will have to be an alternative hypothesis. So here, sigma is not equal to 0.18, goes under the alternative hypothesis, and that's also the claim. The null always has the equal sign in it, so it'd be sigma equal to 0.18. And now step number 4 is your level of significance. In this case, it was 0.05. Because it's given to you in the problem. All right, now step number 5 is calculating the test statistic. Now we're told we have a simple random sample of 21 cans of the soda drink. So N is 21. We're told those volumes have a mean of 12.19 ounces. That's not needed in this particular situation. And a standard deviation of 0.12 ounces. That we need to know. That's the one we're going to need to use. And then let's get our degrees of freedom. That's, of course, N minus 1. N is 21, so 21 minus 1 will be 20 degrees of freedom. And sigma is from the null hypothesis, 0.18. Okay. Now let's calculate the chi-square test statistic. All right, so in this case, chi-square is this. N minus 1 times S squared divided by sigma squared. N is 21, so 21 minus 1 times S, which is 0.12, that's going to be squared, divided by sigma, that's 0.18. That 2 is going to be squared. All right, so now, let's see. Left parentheses would be 21 minus 1, close parentheses, times 0.12, and then that's going to be squared, divided by 0.18. That's going to be squared. And then hit enter. To 3 decimal places, this will be 8.889. 8.889. That's the test statistic for this, for our sample statistics here. Step number 6 is finding the p-value. Now let's look at our alternative hypothesis here. It says less than. Less than points to the left, so that means we have a left tail test. And because we have a left tail test, based on this, we have to use this format. Chi-square CDF, negative with a bunch of 9s, then your test statistic, then degrees of freedom. Follows that format for a left tail test. So that means our p-value is this, chi-square CDF, then negative with 6 9s or as many 9s as you want. Make sure you have a negative sign in front. Test statistic is 8.889. Degrees of freedom, 20. Okay. So in this case here, we do second bars, go down to chi-square CDF. The lower would be the negative with 6 9s or as many 9s as you want. Then enter. The upper limit is that test statistic of 8.889. degrees of freedom, that'd be 20. Hit enter 3 times. This is going to be your p-value. And I think they say 4 decimal places in the homework. This will be 0.0158. Now, I do want to warn you how many decimal places they want you to round off to. Pay close attention to the directions in the homework in my math lab. If they say 3 decimal places, then you round it to 3 decimal places. If they say 4 decimal places, round it to 4 decimal places. Okay? And now step number 7 is the decision rule. If our p-value is less than or equal to alpha, reject the null hypothesis. The p-value is 0.0158, and the alpha level from step 4 is 0.05. Well, notice that 0.0158 is less than 0.05. It does satisfy the decision rule, so that means we need to reject the null hypothesis. And then finally, step number 8 is to write our conclusion using simple non-technical terms here. The claim was the alternative hypothesis. We rejected this null. So that means that we have sufficient evidence to support the claim. So that means there is sufficient evidence to support the claim that the population of volumes has a standard deviation less than 0.18 ounces. Okay. All right. All right, so that does conclude this video on section 8.4 dealing with testament claim about a standard deviation or variance.